Okay, guys, let me start giving you homework. That is because you guys are not, I think, practicing. So this is a ethylene molecule. Now, the way we have done it for water molecule, we have done the SALC using 1s orbital from 2 hydrogen atoms. Here also, I want you to form the SALC using 2 px orbital sitting on each carbon atom of ethylene. Right. Now, of course, the Cartesian coordinates, the way we have chosen, this is a planar molecule, and this is z-axis is along this principal axis C2, and therefore the x-axis has to be perpendicular to this molecular plane, right? So therefore molecule is going to be on the yz plane, and pi orbitals are going to be forming from the px of this carbon, px of this carbon. Okay, so your job is to find out the form of the SALCs for the pi orbitals of this ethylene molecule using the px orbital of 2 carbon atoms. So this px as the bases. So these are going to be the choice of bases, and based on this form the SALCs for the pi orbitals of ethylene. Okay, so that's what I want. I hope you'll be able to do it, and please do it. Yeah. Okay, so next I'm moving to the ammonia molecule, because this is there in the syllabus, C3b point group. So this is the last topic. I think we are going to go construction of molecular orbitals of ammonia. Here we will follow exactly the same notion, the way we have done it for the water molecule. First, we have formed the SALC using the two function like 1s A, 1s B for the 2 hydrogen atoms. Here also we have to first initially find out the ligand group. Now exactly in the same notion what we did for water molecule, here these 3 hydrogens are of same type, and therefore they are going to form the ligand group. And of course a central atom is here nitrogen. You can say nitrogen is a subatomic group. So what we will do is first to form the SALC based on the 1s orbital of these hydrogen atoms, and according to their symmetry we'll combine those SALCs with the atomic orbitals of nitrogen. Okay. So yes, construction of SALCs, then we need to find out the basis. Now, as we are going to form the SALC using the hydrogen atom, so natural choice is going to be 1s orbital of 3 hydrogen atoms. So this is just part A. So 1 is A, 1 is B, and 1 is C. These are the 3 1s orbital is my choice of basis to form the SALC. Okay. Now we are, one important thing is that the choice of Cartesian coordinates. Now I have taken x-axis in such a way that here one of the hydrogen is sitting on the x-axis. So it's along this, and because z is perpendicular to this xy plane and passing through the nitrogen. Okay. So with this choice of Cartesian coordinates and the basis, 1 is A, 1 is B, and 1 is C, we are going to construct the reducible representation first. Okay, now here you can do it in 2 ways. First thing, you can construct the matrix representation for corresponding to each operation and find out the character. But I'm going to go in a little simpler way, that unshifted function rule. Right here, if the function changes the position, then contribution will be 0. If it is remains on the same place, then contribution is going to be 1. Now here this function is not going to change sign, so therefore that part is not going to be here. Okay, so now if we think about this performing operation of C3B point group, let's say identity. Now what is going to be the character? Now for identity, none of them are going to change the position. So therefore contribution is going to be 1 from here, 1 for this, and 1 for this function. So total is going to be 3. Right? Now if I go for C3 along Z, so that is Z is passing through this and perpendicular to this XY plane. And if we do C3 either clockwise or anti-clockwise, you realize is that all of the functions are going to, or the bases are going to change their position. So their contribution from each of them is going to be 0. So when you do C3 along Z, contribution of this function is going to be 0. From this function is going to be 0 because this is also shifting and this is also shifting its position. So therefore, this is going to be, character is going to be 0 for C3. Now if I go for sigma V, let's say XZ along this, so then what happened is that like this this function 1 is A remains unchanged, or its position remains unchanged, whereas this 1 is A and 1 is B, there shifting the position. So therefore the contribution from this and this are going to be 0, but this is going to be not 0, so that is going to be 1 actually. So that is sitting on the XZ plane, right? So contribution from this is going to be 1, for this is going to be 0 because it is going to be reflected by this plane, and this is going to be 0. So total is going to be 1 plus 0 plus 0, that is going to be 1. Now this gives the total representation using 3 bases. Now if we reduce this systematically using the reduction formula, what we have learned earlier, then it will give what are the irreducible representations are going to be involved in this total representation. Right? And that is very simple. If you look at the character table of C3V, you will realize that that is going to be your A1 and E. That is because A1 are going to be 1, 1, 1, and E is going to be 2, minus 1, 0. Therefore, if you add them, so you are going to get 3, 0, and 1. So that's why you can easily span this just by doing the addition of these two representations. So you'll get exactly the same answer if you do it by reduction using the reduction formula. Okay, so what does that mean? This means that if you take this basis, one is A, one is B, and one is C, I'm going to form SALCs, 3 SALCs of course, of 2 types. Right, one of them is going to be A1 type, and the 2 of them are going to be E type. So they are doubly degenerate. Okay, so now our job is to find out what is going to be their shape or how they look like. Okay, yeah. So again, we'll follow the same procedure the way we have done it for water molecule. That we'll be using the projection operator. So what you have already seen, this projection operator. Using the projection operator, we will be finding out the different symmetry SALCs. Like here, if I want to go for this of A1 type, SALC of A1 type, then my projection operator of E1. Then operating on a basis function, I am taking only one function because this is one dimension. Okay, so so it does like this. This is my function, one is A, so it is here. Now I have to operate all the operations on this basis function. Whatever the resultant I am going to get, that I have to multiply with the character of A1 representation, right? Then when we after multiplication, when we sum them up over all the operations, we are going to get the SLC expression, right? So let's do it here, then it will be easier for us to understand, right? Okay, the choice of basis is for this or the basis on which I'm going to apply the operations are going to be 1 is A. So this is the function, it's a spherical function of 1 is A, right? Now if I perform these operations, now look at here, I need to mention here there's operations of C3V point group. I have splitted them, the class I have separated them because then my performing operation will be much easier to visualize, right? So two operations C3.1 and C3.2, I have separated them, although they are having the same character. Now for this is sigma V. A stands for that I am taking this plane which contains the 1 is A. So that means that is basically XZ plane, sigma V XZ, and that is so A stands for containing 1 is A function. Now sigma VB means that this is going to be the plane like that. That is basically the one which contains the function 1 is B. And exactly in the same fashion, the sigma V C, if I take, then this is going to be the plane, this one, which contains the 1C function, right? So that is the idea of splitting in this way. So this helps us in performing the operations. Okay, so now if I take this as a function doing the operations, each operation, right, identity, what I am going to get? I am going to get so now taking this basis, I perform all the operations one by one, what we get the resultant on this. So if I perform identity, this function remains 1 is A, okay? So that is going to be 1 is A. Now if I perform C3.1, so that means only once I rotate the 120 degree, then this 1 is A function going to change it to 1 is B. So that is going to be 1 is B. Now if I perform again one more C3, so that means 120, so that is C3.2. So then 1 is A was first time it was here, then it is going to go there, so that means that is going to be 1 is C. 1 is C. Okay, now if I perform sigma VA means this is the XZ plane which contains the 1 is A, then this function, it remains on the plane, right? Or this function is not going to change, right? So therefore this is going to be remaining 1 is A. Now if I take sigma VB, this plane, then 1 is A becomes 1 is C. So this is going to be 1 is C. Okay. Now if I do sigma VC, so that means this is the plane, then you can think about that this 1 is A function is going to change it to 1 is B. Okay. Now character for A1, if you look at the character table for C3b, all are going to be 1. That is going to be 1. Right. Now I need to multiply this with this character, so I get this one. Right. So what is then it is going to be? Multiplication gives me 1s A. Right. So I'm multiplying this into this like that. This into this. This into this. This into this, and this into this. So all of them are going to be exactly same without changing the value or the sign, because it's multiplication with 1 multiplied by 1. Right. So that is going to be 1sc, and this is going to be, so this is 1sc. Now this is going to be again 1sa. It's going to be 1sc, and this is 1sb. Okay. So now next job is going to this one, sum over all the operations. So I'm doing all the operations. If I do sum them up, then I'm going to get the form of this. Right. So what is that? Now that is going to be this one. So it is going to be all the functions are going to be appearing twice. So this is 1sa and this is 1sa. So I'm getting 2 of them. 1sb, I'm getting 2 of them. And 1sc, I'm getting 2 of them. Right. So therefore, this is going to be 2 into 1sa plus 1sb plus 1sc. Okay. Now, as you of course realize that this is not normalized, you have to normalize this. So normalization procedure, you know, we have already discussed it. So if you use the normalization procedure, then after normalization, you are going to get the function 1 by square root of 3. That is because you are taking the coefficient like this is 1, this is 1, or this is 1. Because if you don't consider 2, just take square of this, square of this, square of this. So you get, and add it up, you get 1. And then you have to take the square root. So therefore, it is going to be 1 by square root of 3. So the final form you are going to get, the SALC of A1 type is going to be 1 by square root of 3 this, and 1 is A plus 1 is B plus 1 is C. Okay. So that is the all in the same page. It's a positive combination. We'll see how it going to be looking like. Okay. Now next one we are going to look at for the E type, right? Doubly degenerate. Now in doubly degenerate, of course, we need two of them. So therefore, we need to consider 2 functions as a basis. Let's consider first one is A itself, right? So just for the sake of this, and then we have to take other function 1 is B to get the other function of E type. So for the timing, if I go for 1 is A, this row remains unchanged. This is just an operation; it's not going to change. So that means this function operating that is going to remain same. But then I need to change the character for E. Right? So that character are going to be, of course, different. So what are the characters are identity. For identity, it is going to be 2. Then for C31 and C32, both are same character, having same character. That is going to be -1. It's going to be -1. And then for the sigma b, it is 0. So for all of them 0, I have just separated them out. So therefore, all of them are going to be 0. This is 0, this is 0, and this is 0. Okay. So now if we multiply, then what do we get? We get 2 into 1 is A then minus 1 is B, minus 1 is C, and this is going to be, these are going to be all 0. So let me erase this. Okay, so these are going to be all 0, so that they are going to vanish. Okay, so therefore, if I now sum them up using the summation over all the operation, what is the function I am going to get? That function is going to be looking like this. So that is 2 into 1 is A minus 1 is B minus 1 is C. Now, again, you have to realize is that this is not normalized. So again, you have to do the normalization. Now, the way, if you think about again, what should be the normalization constant, is very simple.